Somewhere in your childhood, you almost certainly asked where everything came from, and somewhere in your childhood, someone gave you the answer. There was a Big Bang. 13.8 billion years ago, the universe burst into being, and before that, there was nothing at all. It is a clean story, and it feels settled. One of the few things about the cosmos we seem to have nailed down. But here is what that story quietly leaves out. No telescope has ever seen the beginning. Every measurement we have shows a universe that was once hot and dense and has been expanding for billions of years, and not one of them shows a first moment. The beginning was never observed. It was inferred by running our equations back to a point where they stop producing physics and start producing infinity, which is the surest sign in all of science that a theory has broken. Pull gently on that single thread, and the beginning of everything quietly comes undone. Get comfortable, hit subscribe if you're new here, because by the end of this, the universe's birthday may feel less like a fact and more like a story we have been telling ourselves in the dark. Now, let's slowly ease into this. Part 1. The birthday everyone believes. Almost everyone alive carries the same picture of how everything started, and most of us have carried it since childhood. There was a Big Bang. Before it, there was nothing. After it, there was everything. The universe has a birthday, and that birthday was 13.8 billion years ago. You have seen the diagram 100 times. The little point of light at the left edge of the page that swells outward into galaxies. The timeline with a sharp beginning and an open-ended future. It feels settled. It feels like one of the few things about the cosmos we actually nailed down. And the strange thing is that the picture is built on real measurements. This is not a fairy tale. When we say the universe is 13.8 billion years old, we are quoting one of the most carefully determined numbers in all of science. The best dataset we have, from a space telescope called Planck that spent years mapping the oldest light in the sky, puts the figure at 13.797 billion years, give or take about 23 million. That is a measurement with a precision that would have seemed insane a century ago. We know the age of the universe to better than 1%. We know it expands too, and we have known that for a long time. In 1929, an astronomer named Edwin Hubble noticed that almost every distant galaxy is moving away from us, and the farther away a galaxy sits, the faster it flees. That is exactly what you would see if the entire universe were swelling, every point drifting away from every other point, like raisins in a loaf of bread rising in the oven. Run that expansion forward, and the universe keeps thinning out. Run it backward, and everything crowds together, hotter and denser the further back you go. We can even see the leftover heat from when everything was packed together. Spread across the entire sky, in every direction you point a sensitive enough antenna, there is a faint glow of microwaves. It is the cooled-down remnant of the fireball the universe used to be, stretched out and chilled by billions of years of expansion, until today it sits at just 2.725 degrees above absolute zero. It is the most perfect example of a particular kind of thermal glow ever found in nature, and it is, in a very real sense, a baby picture of the cosmos. When you watch the static between channels on an old television set, a tiny fraction of that snow is this ancient light falling on the antenna from the early universe. There is a piece of history here that almost nobody remembers, and it matters for everything that follows, so let me tell it. The phrase Big Bang was not coined by a believer. It was coined as an insult. In the middle of the 20th century, cosmology was split into two warring camps, and the leader of the side that opposed the idea of a cosmic origin was a brilliant British astronomer named Fred Hoyle. Hoyle could not stomach the notion that the universe had a single, fiery beginning, and in 1949, during a radio broadcast, he reached for a mocking nickname for the rival theory, calling it, dismissively, this Big Bang idea. The name stuck, ironically, to the very theory he was trying to ridicule, and his own preferred picture faded from view. What was Hoyle's picture? It was called the steady-state theory, and it was, in its own way, the original no-beginning model. Hoyle, along with Hermann Bondi and Thomas Gold, proposed that the universe had always existed and always would, looking essentially the same at all times. As the cosmos expanded and galaxies drifted apart, they imagined new matter being created continuously in the gaps, just enough to keep the overall density constant so that the universe was eternal and unchanging on the large scale. There was no beginning, no birthday, no moment of creation. The universe simply always was. For a couple of decades, this eternal universe was a serious scientific rival to the Big Bang, championed by some of the finest minds of the era. The steady-state theory lost, and it is important to be clear about why it lost, because the loss is real and the modern no-beginning models all had to learn from it. It lost because of the cosmic microwave glow. An eternal, unchanging universe has no reason to be bathed in the cooled remnant of a hot, dense phase, because in the steady-state picture there was no hot, dense phase. But when that microwave glow was discovered in the 1960s, almost by accident, it was exactly what a hot early universe would have left behind, and exactly what the steady-state theory could not explain. The eternal universe of Hoyle and his colleagues died, and the Big Bang won. I tell you this so you understand the rules of the game. Any modern theory that wants to do away with the beginning cannot simply declare the universe eternal and unchanging. It has to accept the hot, dense phase, accept the microwave glow, accept everything the evidence demands, and find its eternity somewhere else, somewhere the old steady-state theory never thought to look. So the evidence is overwhelming, and I want to be honest about that from the very first minute, because this video is going to take you somewhere unsettling, and I do not want you to think it rests on shaky ground. The universe was once hot. The universe was once dense. The universe was once far smaller than it is now, and it has been expanding for billions of years. None of that is in question. The cosmic glow, the fleeing galaxies, the measured abundances of the lightest chemical elements forged in the first few minutes, all of it points the same way. There really was a hot, dense early phase, and we really do live in the aftermath of it. Here is the question, though, the one that is going to quietly take this entire picture apart over the next 2 hours. Does any of that evidence actually say the universe began? Look closely at what we measured. We measured an expansion, we measured a temperature, we measured the ages of the oldest stars, and the leftover heat and the speed of the galaxies. Every one of those tells us the universe was once compressed and has been growing ever since. Not a single one of them tells us there was a first moment. The beginning is not something we observed. The beginning is something we inferred. By taking the expansion we can see and running it backward in our equations past the point where we have any evidence at all the way down to a moment we labelled time zero. And when you take general relativity, our best theory of space and time and gravity, and you run it back to that moment, it hands you something disturbing. It hands you a singularity, a point of infinite density and infinite temperature and infinitely curved space, where everything that exists is crushed into no volume whatsoever. For about 100 years, that singularity has quietly been treated as the birth certificate of reality, the instant of creation, the first tick of the only clock there is. This video is about a single, vertiginous possibility, taken seriously by serious physicists, published in serious journals, and almost never explained properly to the people who would find it the most astonishing. The possibility is this: that singularity may not be a beginning at all. It may not be the first moment of anything. It may be something far stranger and far more disturbing than a birthday. The universe you live in, the one with the famous origin story, might never have been born. We tend to assume that everything that exists must have started somewhere, because everything in our experience does. You had a beginning. This planet had a beginning. Your morning had a beginning. The intuition that existence must come with a start is one of the most fundamental things the human mind believes. But the universe is not obligated to obey the intuitions of one species of primate on one small world. And over the next 2 hours, we are going to meet several detailed, mathematical descriptions of a cosmos that simply always was. Some of them stretch time infinitely into the past. Some of them loop forever with no first loop. One of them erases the very idea of a first moment so completely that asking for one becomes a kind of nonsense. If even one of these pictures is correct, then the oldest question human beings have ever asked, the question that sits underneath every creation myth and every theology and every late-night childhood thought about where everything came from, may not have an answer. Not because the answer is hidden, but because the question was the wrong question all along. So settle in, and let us start where everyone starts, with a birthday nobody ever actually witnessed. Part 2. The number is real, the beginning is not. I want to slow down on one move, because the entire rest of this video balances on it, and it is the kind of move that is easy to nod along to and then completely miss. The number 13.8 billion years is real. The beginning attached to that number is not measured, it is assumed, and once you see the gap between those two things, you cannot unsee it. Think about what a telescope actually does when it looks back in time. Light travels fast, but not infinitely fast. So when you look at something far away, you are seeing it as it was when the light left it. Look at the sun, and you see it as it was 8 minutes ago. Look at the nearest large galaxy, Andromeda, and you are looking 2.5 million years into the past. The farther out we look, the further back in time we see, and our best telescopes can look very far indeed, back to when the universe was only a few 100 million years old, an era of the first galaxies just switching on. But there is a wall. There is a point beyond which no telescope can ever see, no matter how powerful, no matter how clever, no matter how far into the future we build them. For the first, roughly 380,000 years after the hot, dense phase, the universe was so hot that it was an opaque fog of charged particles, and light could not travel freely through it. Light was trapped, scattering endlessly, the way it does inside the body of the sun. Only when the universe cooled enough for atoms to form did that fog clear and light finally stream out across space. That first freed light is the microwave glow we see today. It is the oldest thing any instrument can ever detect, and it comes from 380,000 years after time zero. So everything before that, the first 380,000 years, the first second, the first fraction of a second, the supposed moment of creation itself, all of it is on the other side of a curtain we can never pull back with light. We do not see the beginning. We have never seen the beginning. We see the aftermath, the cooled glow, the fleeing galaxies, and we extrapolate the rest. We take the expansion we can measure, and we wind the film backward, frame by frame, past the curtain, past the first second, all the way to a moment our equations insist must be there. That extrapolation is reasonable. I am not saying it is foolish. If you watch a ball flying up and slowing down, it is reasonable to conclude it was thrown from the ground a moment ago, even if you did not see the throw. But notice the difference. When you wind the cosmic film all the way back to time zero, the equations do not show you a tidy little starting point, a ball resting on the ground. They show you a place where every quantity you can calculate runs off to infinity. The density becomes infinite, the temperature becomes infinite, the curvature of space becomes infinite. Everything that exists gets squeezed into a region of exactly zero size. Now, infinity is not a number. This is the thing that physicists know in their bones, and that almost never gets communicated to everyone else. When a physical theory starts producing infinities, that is not the theory describing some incredibly intense real thing. That is the theory failing. It is the mathematical equivalent of a car engine throwing smoke and grinding to a halt. An infinite answer is the universe's way of telling you that you have driven your theory past the edge of where it works, into territory it was never built to describe. We have seen this exact pattern before, more than once. Before we understood the atom, classical physics predicted that an atom should collapse in a fraction of a second, the electrons spiraling into the nucleus and radiating infinite energy. That infinity was not a real catastrophe happening inside every atom. It was a signpost telling us that classical physics breaks down at the scale of the atom, and that a deeper theory, quantum mechanics, was needed. The infinity was a confession of ignorance, dressed up as a prediction. So here is the gap, laid out plainly. The measured part is the expansion and the cooling, solid as anything in science. The inferred part is winding that expansion back to a first moment. And right where that inferred first moment is supposed to sit, our equations stop producing physics and start producing infinity, which is the surest sign we have that we have left the realm where those equations mean anything. The beginning, in other words, lives entirely in the region where our best theory has already broken down. We are most confident about the birthday in exactly the place where we understand the least. It is worth dwelling on just how routine this pattern is in the history of science, because it should change how nervous you feel about trusting the singularity. Every time physics has run into an infinity, that infinity has turned out to be a marker of ignorance rather than a feature of the world. When physicists first calculated how much energy a hot object should radiate, the math predicted infinite energy at short wavelengths, a result so absurd it was nicknamed the ultraviolet catastrophe. The infinity was not real. It was a sign that classical physics failed at small scales, and resolving it gave birth to quantum theory itself. When physicists calculated the energy of an electron interacting with its own electric field, they got infinity again, and again the infinity was a sign of a theory pushed too far, tamed only by the deeper framework of quantum field theory. The track record could not be clearer. Infinities are not discoveries, they are confessions. So when general relativity hands us an infinity at the first moment of the universe, the lesson of history is not to bow down before it as the instant of creation. The lesson is to suspect, strongly, that we have once again driven a theory past its limits, and that a deeper theory waiting to be found will smooth the infinity away into something finite and comprehensible. The only difference is the stakes. In the other cases, the thing on the far side of the infinity was the structure of the atom or the behavior of an electron. In this case, the thing on the far side of the infinity is the answer to whether the universe began at all. There is a subtle psychological trap built into the way we are taught the Big Bang, and it is worth naming directly. We are shown the timeline, the expanding diagram, the story that runs from a first moment to the present, and the whole presentation has the confident, finished feel of settled knowledge. It does not come with an asterisk. Nobody draws the diagram and then says, by the way, the leftmost point, the moment of origin, is the one part of this picture we have no evidence for and no working theory of. The certainty of the diagram is borrowed from the parts we do understand, the expansion and the cooling, and then quietly extended to the one part we do not. The beginning gets to ride on the credibility of everything that came after it. Once you notice that, a great many confident statements about the origin of the universe start to look different. When someone says the universe began 13.8 billion years ago, the first half of that sentence, the universe began, is a philosophical claim resting on a broken equation, while the second half, 13.8 billion years ago, is a precise measurement of how long the expansion has been going on. The sentence smuggles an assumption inside a fact and says them in the same confident breath so that the assumption inherits the authority of the fact. Pulling those two halves apart is the single most important thing this video will ask you to do, and once you have done it, you cannot put them back together as easily as before. This is why so many cosmologists have spent decades refusing to treat the singularity as a real event. To them, calling it the beginning is like driving toward a horizon, watching your map dissolve into blank paper at the edge, and declaring that the world itself must end where your map runs out. The map is not the territory. The place where our description fails is not necessarily the place where reality begins. It may just be the place where our knowledge does. And once you accept that the beginning is a feature of a broken equation rather than a measured fact, an enormous door swings open. Because if the singularity is not a real wall, but a gap in our understanding, then something might lie on the other side of it. There might be a before. The universe might extend past that moment in ways our current theory simply cannot follow. The birthday nobody ever witnessed might not be a birthday at all. To find out what could be hiding behind the curtain, we have to go right up to the edge of where our physics dies and look at exactly how it dies. Part 3. The singularity is a confession. Let me take you to the edge, not metaphorically. I want you to actually make the journey backward in time with me, down toward time zero, and feel the exact moment where the description of reality stops working because it is one of the strangest places in all of physics, and almost nobody gets shown it directly. You are standing in the universe, as it is now, enormous and cold and quiet, galaxies scattered like dust across an immense darkness. Now we begin to run time backward, and everything starts to fall together. The galaxies stream toward one another. The darkness between them shrinks. The temperature of empty space, which is just below 3 degrees above absolute zero today, begins to climb. Stars stream back into the gas clouds they formed from. The universe grows brighter and hotter and more crowded with every step backward. Keep going. The galaxies dissolve into the smooth hot plasma they condensed out of. The whole of space is now glowing, a uniform fire in every direction, hotter than the inside of any star. Atoms come apart into bare nuclei and free electrons because it is far too hot for them to hold together. Keep going. The nuclei themselves come apart into individual protons and neutrons. The temperature is now in the billions of degrees and still climbing as the universe shrinks toward the first second. Keep going. The protons and neutrons melt into a soup of their constituent quarks, a state of matter so hot and dense it existed only in the universe's first instance. You are now a tiny fraction of a second from time zero, and the numbers are getting violent. And here, right here, just before you reach the supposed first moment, something happens to the mathematics itself. The density, which has been climbing steeply this whole time, stops being a large number and starts heading for infinity. The temperature does the same. The curvature of space, the very bending that we call gravity, spikes toward infinity as well. Every equation you would use to describe what happens next stops returning answers and starts returning that one meaningless word, infinite. You have arrived at the place where general relativity goes blind. There is no next frame of the film. The map simply ends, and beyond its edge is not a wall, not a cliff, not a door. It is blank paper. It is the place where the theory has nothing left to say. That blank place is what we call the singularity. And I want to be precise about what it is and is not, because this is the crux of everything. A singularity in physics is not an object. It is not a tiny dense thing sitting at the start of time. It is a breakdown. It is the symptom of a theory being pushed past its limits. General relativity is a theory of smooth, continuous space and time, and it works beautifully across an astonishing range of conditions, from the orbits of planets to the bending of light around galaxies to the ticking of clocks on satellites. But it knows nothing about quantum mechanics, And at the scales near time zero, quantum mechanics cannot be ignored. The singularity is the sound general relativity makes when it collides with a regime it was never built to handle. There is a beautiful irony buried in the history here. In the 1960s and 70s, a young Stephen Hawking, working with the mathematician Roger Penrose, proved a set of theorems that seemed to make the beginning unavoidable. The Penrose and Hawking singularity theorems showed that if general relativity is correct and matter behaves in reasonable ways, then an expanding universe like ours must trace back to a singularity. For a while, this was taken as proof that the universe had a beginning, a genuine mathematical demonstration that time started. But look carefully at the fine print of those theorems, because it changes everything. The theorems assume that general relativity holds all the way down, right into the regime of infinite density. They prove that if you trust general relativity completely, even where it is screaming infinities at you, then there must be a singularity. In other words, they prove that general relativity predicts its own failure. That is not the same as proving that reality began. It is proving that our theory breaks, and breaks in a specific, unavoidable way, precisely at the moment we most want answers. Hawking himself, later in his life, became one of the people most interested in getting rid of the beginning entirely, as we will see. To feel why general relativity must fail there, you have to understand the collision at the center of all of modern physics, the one we have never managed to resolve. We have two supremely successful theories of reality, and they do not get along. General relativity describes gravity, space, and time, and it governs the very large, the realm of planets and stars, and galaxies and the universe as a whole. Quantum mechanics describes the very small, the realm of particles and atoms, and the strange probabilistic flickering of the subatomic world. Each is fantastically accurate in its own domain. Each has passed every experimental test thrown at it for a century, and they are mathematically incompatible. When you try to force them to describe the same situation, they produce nonsense, infinities, contradictions. In almost every situation in the universe, this incompatibility never matters, because the two theories rule separate kingdoms. Gravity is absurdly weak at the scale of particles, so quantum physicists can ignore it. And quantum effects are negligible at the scale of planets, so relativists can ignore them. But there is one place where the very large and the very small are forced into the same room, where an enormous amount of mass energy is crushed into a quantum-sized space, and where you therefore need both theories at once. That place is the first instant of the universe. The singularity is precisely the point where gravity and the quantum world collide head-on, and the infinities it produces are the screaming sound of our two best theories failing to agree. To know what really happened there, we would need a theory that unites them, a theory of quantum gravity, and we do not yet have a finished one. So the singularity is not a birth certificate. It is a confession. It is general relativity admitting, in the only language it has, that it does not know what happens at the first moment, and cannot know because the first moment lives in the quantum regime where general relativity does not apply. To find out what actually happens there, we would need a theory that combines gravity with quantum mechanics, a theory of quantum gravity. We do not have a finished one, but we have several serious candidates, and here is the thing that should make the back of your neck prickle. Almost every one of those candidate theories, when you apply it to the moment of the singularity, does the same remarkable thing. It removes the beginning. There is a reason almost every candidate theory of quantum gravity does this, and it is not coincidence or wishful thinking. The infinities of the singularity come from treating space and time as a perfectly smooth continuum that can be compressed without limit, down to literally zero size. Every serious attempt to quantize gravity, in one way or another, puts a flaw under that compression. Some, like loop quantum gravity, do it by making space itself grainy, with the smallest possible unit. Others, like string theory, do it by replacing point particles with tiny, extended objects that cannot be squeezed past a minimum length. The details differ wildly, but the consequence converges. If there is a smallest meaningful length, or a smallest meaningful volume, then infinite density becomes impossible, because you can never finish the infinite squeezing the singularity requires. Remove the possibility of zero size, and you remove the singularity, and the moment you remove the singularity, the supposed wall at the beginning of time turns into a doorway you can, at least in principle, see through. That convergence is one of the quiet reasons physicists have grown comfortable doubting the beginning. It would be one thing if only a single fringe theory predicted the singularity should be replaced by something finite. But when nearly every approach to the problem, built on completely different foundations, points the same way, toward a beginning that dissolves into a bounce or a smooth cap, or a passage to something earlier, you start to suspect that the dissolution is the robust prediction, and the singularity was only ever an artifact. The artifact was general relativity, magnificent but incomplete, drawing a sharp edge where a deeper theory would draw none. The singularity, the one solid wall that seemed to mark the start of everything, turns out to be the place where our physics ends, not necessarily the place where the universe begins. It is the edge of the map, not the edge of the territory. And the moment you have a theory that can see past the edge of the old map, you have to ask the most dangerous question in cosmology. What if there is a before? What if the universe did not start at the singularity, but pass through it from something that came earlier? Before we can follow that question into the models that take it seriously, we have to meet the one piece of physics that fights back hardest against it. There is a theorem that says, no matter how clever you are, the past cannot go on forever. Part 4. The wall that says the past must end. Every good story needs something standing in the way, and the idea that the universe never began has a formidable obstacle blocking its path. It is not a vague philosophical objection. It is a sharp, specific, mathematical result proved in 2003 by 3 physicists named Arvind Borde, Alan Guth, and Alexander Vilenkin. It is usually just called the BGV theorem after their initials, and any honest treatment of the no-beginning idea has to climb over it. So let us understand exactly what it says, and, just as importantly, what it does not say. The theorem asks a simple-sounding question. Suppose you have a universe that, on average, has been expanding throughout its history. Can that universe have an infinite past? Can you keep following its history backward forever, or must you eventually hit a boundary, a starting edge, beyond which the history cannot be extended? And the answer Borde, Guth, and Vilenkin proved is stark. If a universe is, on average, expanding, then its history cannot be infinite into the past. It must have a boundary. There must be a beginning to the expansion. What makes the theorem so powerful is how few assumptions it needs. Earlier arguments for a beginning leaned on general relativity, and we just saw that general relativity breaks down near time zero, so those arguments could be dismissed as artifacts of a failing theory. But the BGV theorem does not actually need general relativity at all. It is a statement about geometry and motion, about the paths that observers trace through an expanding space. As long as the average expansion over the whole history is greater than zero, the theorem bites. It does not care about the details of what matter is doing or which theory of gravity you use. That generality is exactly what makes it such a wall. Alexander Vilenkin, one of the 3 authors, has been blunt about what he thinks it means. He has written that, with the theorem in hand, cosmologists can no longer hide behind the idea of an eternal universe. He has said that all the evidence we have points to the universe having a beginning, and that there is no escape, that scientists cannot avoid facing the problem of a cosmic origin. Coming from one of the people who proved the result, that is a heavy statement. If you want to believe the universe never began, you have to reckon with the fact that one of the sharpest minds in cosmology looked at his own theorem and concluded the opposite. So, is that the end of the story? Did three physicists in 2003 simply prove that the universe had to begin and everything else in this video is wishful thinking? No. And the reason is hidden in three small words that I have repeated several times on purpose. On average, expanding. The theorem only applies to a universe whose expansion, averaged over its entire history, is positive. That condition sounds almost too obvious to matter, because our universe is expanding right now, and has been for as long as we can see. But it is the crack through which every no-beginning model escapes. Think about what it would take to violate the condition. You would need a universe that was not, on average, always expanding. A universe that, somewhere in its past, was contracting instead of expanding. A universe that perhaps shrank, reached some minimum, and then began to grow, so that the expansion we see today is only the most recent chapter, and the average over all of history is not simply positive. The moment you allow a phase of contraction before our expansion, the theorem's central assumption no longer holds, and its conclusion no longer follows. The wall has a gap in it, and the gap is shaped exactly like a universe that fell inward before it blew outward. It is worth being very concrete about that gap, because it is easy to wave at and hard to feel. Picture the entire history of our universe as a single line drawn through time, with the present on the right and the past stretching to the left. The BGV theorem asks whether you can extend that line infinitely far to the left, and it proves that if the line is sloping the same way the whole time, always expanding, then no, the line must have a left end, a beginning. But now imagine the line is not straight. Imagine that, far to the left of where we can see, it bends. Imagine the universe was contracting, the line sloping the other way, before it reached a turnaround and began the expansion we observe. The average slope is no longer simply positive. The theorem's single assumption is broken, and the line, instead of stopping at a left end, can curve back and continue, perhaps forever, into a contracting phase that came before our expansion. That bend in the line is where every bounce and cyclic model lives. The theorem does not forbid the bend. It only forbids a line with no bend at all. There is something almost poetic about how narrow the escape is. The theorem is one of the strongest results in cosmology, and yet the entire question of whether the universe began comes down to three words: on average expanding, and whether the universe honored that condition for all of its history, or violated it in some distant, unobservable past. We cannot currently see far enough back to know. The contraction phase, if it existed, lies behind the same curtain that hides the first instant. So the theorem does not settle the question. It refines it into the sharpest possible form. Did the cosmic history slope the same way forever, or did it once bend? There is a second escape route, too. The theorem is a classical result, a statement about smooth geometric paths. Near the supposed beginning, in the quantum gravity regime, the very notion of a smooth path through space and time may dissolve. If space and time themselves become fuzzy, foamy, quantum things at the smallest scales, then the clean geometric assumptions the theorem relies on may simply not apply, and the proof loses its grip. The theorem is rigorous within its domain, but its domain is the smooth classical world, and the beginning lives in the quantum one. This is why the no-beginning idea is hard rather than easy, and I want to be fair to both sides here. The BGV theorem is real, and it is not a trick. It genuinely shows that the simplest possible eternal universe, one that just expands forever into the past and future at a steady average rate, cannot work. You cannot have a universe that was always expanding and also always existed. Something has to give. Either the universe began or its history includes something other than steady expansion, a contraction, a bounce, a cyclic phase, a quantum regime where the rules change. It is also worth knowing that not everyone reads the theorem the way Vilenkin does, including people who respect it completely. The disagreement is not about whether the theorem is correct, because it plainly is within its assumptions. The disagreement is about how much those assumptions actually constrain reality. Some physicists argue that the averaged expansion condition is exactly the kind of thing that fails in the quantum regime near the supposed beginning, so that the theorem, while true, simply does not apply to the only era where the question of a beginning is decided. Others point out that the theorem says nothing about what happens at the boundary it predicts, whether that boundary is a true beginning, a smooth cap, or a handoff to a contracting phase on the other side. The theorem proves there is a boundary to past-directed expansion. It does not prove that the boundary is the start of existence. That distinction is subtle, but it is everything. Imagine walking backward along a road and discovering that the road ends at a river. The BGV theorem is the proof that the road ends. It is silent on whether the river is the edge of the world or simply a crossing into different terrain. Vilenkin looks at the river and sees the edge of the world. The builders of bounce and cyclic models look at the same river and see a crossing, a place where smooth classical expansion gives way to something else, a contraction, a quantum bridge, a phase the theorem was never equipped to describe. Both are looking at the same rigorous result. They simply disagree about what lies on the far bank, and the theorem itself refuses to take sides. So the theorem does not close the door on a universe without a beginning. What it does is tell you exactly what kind of door you have to walk through. If you want a cosmos that never began, you cannot have a boring one. You need a universe with a more dramatic past than simple expansion. You need it to have fallen before it rose, or cycled before it settled, or emerged from a quantum state where even the word before changes meaning. The wall is real, but it has specific gaps, and the rest of this video is a tour of the models that have found their way through them. The first and most direct of those models takes the singularity, the supposed first moment, and turns it into something nobody expected. Not a birth, a bounce. Part 5. The bounce. The simplest way to give the universe a past is to refuse to let it crush down to a point, and there is a serious, detailed theory of physics that does exactly that. It is called loop quantum cosmology, and it grows out of one of the leading attempts to unite gravity with quantum mechanics. The central figures in developing it include the physicists Abhay Ashtekar and Martin Bogerwald, and the key result that turns the Big Bang into something else was worked out in the mid-2000s. What it proposes is so simple to state and so strange to absorb that it is worth sitting with. The idea begins with a single, radical assumption about space itself. In the world we experience, space seems perfectly smooth and infinitely divisible. You can imagine cutting any distance in half, then in half again, forever, never reaching a smallest possible length. Loop quantum cosmology says that intuition is wrong. It says space, like matter, comes in discrete chunks. There is a smallest possible unit of area, a smallest possible unit of volume, a graininess to the fabric of reality far below anything we could ever see. Space is not a smooth sheet. It is something closer to an unimaginably fine chainmail, woven from tiny loops, and you cannot squeeze it tighter than the size of its links. Now think about what that does to the journey we took backward in time, the one that ended in a singularity. As you compress the universe smaller and smaller, the density climbs, exactly as before. But in this picture, you cannot compress space below the size of its smallest grains. And as you approach that limit, something unprecedented happens to gravity. Gravity, which is attractive in every situation we have ever observed, which pulls and never pushes, which holds you to the floor and holds the galaxies together, flips. At the unthinkable densities near the smallest scale, the quantum nature of space makes gravity become repulsive. It stops pulling everything together and starts violently shoving everything apart. The collapse does not reach a point. It reaches a floor, a maximum possible density, roughly what is called the Planck density, a number so large it is almost a joke to write down, around 10 to the 96th kilograms packed into every cubic meter. And at that floor, the repulsion takes over and flings everything back outward. The universe does not begin, it rebounds. The Big Bang was not a birth, it was a bounce. It helps to know where this strange idea of grainy space actually comes from, because it is not invented just to kill the singularity. It falls out of one of the most serious attempts to build a quantum theory of gravity, called loop quantum gravity. The core idea of that theory is to take general relativity's central insight, that gravity is the geometry of space and time, and to apply the rules of quantum mechanics to geometry itself. When you do that, when you quantize space, the way we quantized energy and matter a century ago, the smooth continuum of space falls apart into a network of discrete relationships, often pictured as a web of nodes and links called a spin network. Area and volume stop being continuous quantities you can divide forever and become things that come in smallest indivisible units, like coins of a currency with no fractions. The smoothness of space, in this picture, is an illusion produced by looking at an incredibly fine-grained structure from very far away, the way a photograph in a newspaper looks like smooth shades of grey until you put it under a magnifier and see it is made of separate dots. Once space has a smallest grain, the singularity becomes impossible almost automatically, and this is the part that makes physicists take the bounce seriously rather than treating it as wishful thinking. You cannot crush an infinite amount of matter into zero volume if there is no such thing as zero volume, if there is a smallest possible chunk of space below which you cannot go. The infinite density of the singularity has nowhere to form. The collapse has to stop at the grain, and the equations of loop quantum cosmology show that when it stops, it rebounds. The bounce is not bolted onto the theory by hand. It emerges from the same mathematics that says space is grainy. That is what gives it weight. It is a prediction, not a patch. Let me put you inside that moment, because it deserves to be felt rather than just described. Imagine you are somehow present in the universe that came before ours, in its final age. Everything around you is falling inward. The galaxies that were once flung far apart are now rushing back together, streaming toward each other across a shrinking sky. The darkness between them is closing. The temperature of space, once near absolute zero, is climbing, first to the warmth of a summer day, then past the boiling point, then hotter, the whole sky beginning to glow a dull red, then orange, then a blinding white as the matter of an entire dying universe crowds in around you. The density is becoming monstrous. Every instinct says this is the end, that everything is about to be crushed into the infinite nothing of a singularity, that the story is over. And then, at the very last instant, at the smallest possible size, the floor holds. Space refuses to be compressed further. The crushing inward pressure does not win. Instead, in a single violent convulsion, gravity reverses, and the entire imploding cosmos is hurled back outward. The white light that was collapsing in on you explodes away in every direction. The density that was climbing toward infinity peels back down. What an observer on the far side would one day measure, billions of years later, as the afterglow of a Big Bang, as the first freed light of a new universe, is in fact the trace of this rebound, the moment the old universe hit bottom and came back. The beginning, seen from the other side, is an ending that did not finish. Hold on to the feeling of that rebound for a moment longer, because there is something in it worth absorbing slowly. The instant we have always called the beginning of everything, the most special moment in the history of reality, the supposed birth of space and time, becomes, in this picture, the least special thing imaginable. It becomes a rebound, a bounce. The same thing that happens when anything compressed too hard springs back, scaled up to the entire cosmos. The moment of creation, the thing every culture has wrapped in reverence and mystery, turns out to be the universe hitting a floor and coming back up, an event with a before and an after. No more a true beginning than the lowest point of a dropped ball is the beginning of the ball. And the previous universe, the one that collapsed to make ours, would have had its own history, its own expansion, long ago, slowing and reversing into the contraction that ended it, its own galaxies perhaps, its own stars, its own long ages of cooling, and then the slow fall back together. Everything that universe ever was got funneled through the bounce and became the raw material of ours, its structure erased in the crush, its matter and energy passed forward into the fireball we call our beginning. We are, in the most literal possible sense, made from the remains of a world that died, recycled through the one moment we mistook for a birth. This is loop quantum cosmology's answer to the riddle of the first moment. There was no first moment. There was a previous universe, contracting where ours expands, a near mirror image of our own cosmic history running in reverse, and it fell inward until the quantum structure of space caught it and threw it back out as us. Time runs continuously through the bounce. There is a before. The singularity, that confession of failure in general relativity, is simply healed by the quantum theory, replaced by a smooth, finite, enormous, but not infinite density, through which the history of the cosmos passes intact. And notice how neatly this slips through the gap in the wall we built in the last part. The BGV theorem only forbids an infinite past for a universe that is, on average, expanding. But a bouncing universe was contracting before it started expanding. The average is not simply positive expansion. The contraction phase is exactly the kind of dramatic past the theorem demands if you want to avoid a beginning, and the bounce provides it. The wall said you could not have an eternal universe that only ever expanded. The bounce says, fine. It did not only ever expand, it fell first. Of course, this raises an obvious and dizzying question, the same one a child asks about any creation story. If our universe bounced out of a previous one, where did that previous one come from? Did it bounce out of one before it? Is it bounces all the way down? An infinite chain of universes each collapsing into the next, with no first link? Loop quantum cosmology, in its simplest form, does not by itself force an answer. The bounce could be a one-time event, a single previous universe collapsing into ours, or it could be the latest in an endless series. To turn the single bounce into a true eternity, a universe that genuinely never began, we need a model where the bouncing never stops, where it is not one rebound, but an unending rhythm of them. We need the universe to be not a one-time firework, but a heartbeat, and that is the next, even stranger idea. Part 6. The endless cycles. If one bounce is possible, why stop at one? This is the thought that drives the cyclic models of the universe, and the most fully developed of them comes from two physicists, Paul Steinhardt and Neil Turok, who spent years building a picture in which the universe has no first cycle at all. They laid it out in a series of papers in the early 2000s, and then in a book with a title that says it all, Endless Universe. Their model is strange, because it reaches into extra dimensions of space to do its work, but the core idea is one of the most elegant in all of cosmology, and it directly answers the question the bounce left hanging. Their starting point comes from a branch of theoretical physics called string theory, which suggests that the three dimensions of space we move through might not be the whole story. There could be additional dimensions, and within that larger space, our entire universe, everything we can see, Every galaxy and star and atom could be confined to a kind of three-dimensional sheet, a membrane, usually shortened to just a brain. Picture our whole cosmos as an enormous flat sheet floating in a higher dimensional space. And now picture a second sheet, a second universe, floating parallel to ours, separated by a tiny gap along a hidden dimension, close but invisible, like 2 pages of a book that never quite touch. In the Steinhardt and Turok model, those 2 sheets are not still. They drift toward each other, drawn together across the hidden dimension by a force between them. They approach slowly, over an almost incomprehensible span of time, and then they collide. And that collision, the moment the 2 sheets slam into each other across the entire extent of space, all at once, everywhere, is what we experience as a Big Bang. The energy of the impact fills our sheet with heat and matter, igniting a new cosmic fire. From inside the sheet, with no way to perceive the higher dimension, it looks exactly like a universe erupting from a hot, dense state. But it was not a beginning. It was an impact. After the collision, the sheets rebound and drift apart again. Our universe, freshly heated, expands and cools, exactly as ours has. Galaxies form, stars ignite, planets coalesce, life, perhaps, appears. Then, over billions and trillions of years, the expansion driven by dark energy stretches the sheet out, thinning it, cooling it, emptying it, until it is a smooth, cold, almost perfectly empty expanse. And in that emptied, flattened state, the stage is perfectly reset. The sheets, still drawn together by the force between them, begin once again to approach. They drift closer over enormous ages. And eventually, they collide again. Another Big Bang. Another universe. Another cycle. What makes this more than just a bounce repeated is how it solves the stubborn problems that the standard beginning could not. Our universe is suspiciously uniform and suspiciously flat. The leading explanation, inflation, says the universe underwent a burst of faster-than-light expansion in its first instance that smoothed everything out. The cyclic model achieves the same smoothness a completely different way, through the slow contraction phase before each collision. The Greek-derived name for that phase is ekpyrotic, meaning out of fire, borrowed from an ancient Stoic idea of a universe periodically consumed and reborn in flame. During the slow approach of the sheets, any wrinkles and irregularities get ironed flat, so that when the collision comes, the new universe is born smooth and uniform across its entire extent. The model does the work inflation does, but without needing a first moment for inflation to start from. The detail in this model that most people find hardest to accept is the extra dimension, the hidden direction along which the 2 sheets approach each other. It sounds like pure fantasy, a convenient invention. But extra dimensions are not something Steinhardt and Turok dreamed up for this purpose. They are a standard feature of string theory, the leading candidate for a unified theory of all the forces, which requires several more dimensions of space than the 3 we move through, dimensions presumed to be either curled up too small to notice, or, in some versions, large but inaccessible to us, because we are stuck to our sheet. The brain picture takes that existing framework seriously and asks what would happen if 2 such sheets, 2 universes, could drift and collide within it. The Big Bang, in that light, is not a metaphysical first cause. It is a physical event, an impact, the kind of thing that can happen more than once, the kind of thing that has no reason to happen only once. And once you accept that a Big Bang can be an impact rather than an origin, the question why only one impact becomes almost unanswerable in the old framework. If the sheets collided once, why not before? What would have held them apart for an eternity and then, at one special moment, let them fall together for the first time? A single collision is actually harder to explain than an endless series of them, because a single collision smuggles a beginning back in through the side door the moment the sheets first started to approach. An endless rhythm of collisions needs no such special first moment. It is, in a strange way, the more natural picture, the one that does not require a mysterious starting event to get the whole process going. And here is the payoff, the thing that makes this a true no-beginning model. The cycles extend infinitely into the past. There was no first collision. Run the history backward, and you do not reach a starting cycle, an origin event, a first impact. You reach another collision before it, and another before that, an unending rhythm of universes being born from the collisions of sheets that have been approaching and colliding and separating forever. The universe is not a firework that went off once. It is a pulse, a heartbeat with no first beat, beating for all of eternity past and continuing for all of eternity to come. There is a question that always comes up at this point, and it deserves a straight answer. If the cycles have been repeating forever, with no first one, then how did we ever get to this cycle? Did an infinite number of cycles have to finish before ours could begin? It is the same worry that has troubled thinkers about an infinite past for thousands of years, and the cyclic model has a clean reply. No cycle had to be the first, and no infinite waiting had to be completed, because there was never a starting line from which the counting began. Pick any cycle you like, and it had a finite number of cycles between it and ours. There is no cycle infinitely far back, just as there is no negative whole number infinitely far below zero, even though the negative numbers go on without end. The series has no first member, and yet every member sits a finite distance from every other. The universe did not have to cross an infinity to reach today. It only had to cross the finite gap between the last cycle and this one, as it always has, cycle after cycle, with no beginning to the sequence and no impossible infinite journey to complete. Sit with what that means for your own existence for a moment. In this picture, everything that has ever happened in our universe, the formation of every galaxy, the birth of the sun, the slow chemistry that led to life, the entire history of your species, the specific chain of events that produced you, listening to this right now, is one frame in a film that has been playing forever. There was no opening scene. There was no first frame. There is no projectionist who threaded the reel and pressed start. The film simply always was, and always has been, running through the projector, cycle after cycle after cycle, with no beginning to the show. The cyclic model has its critics, and the deepest objection to it is one we will face head-on later, because it is the same objection that haunts every cyclic picture of the cosmos. It has to do with disorder, with the relentless one-way increase of messiness that physicists call entropy, and with a problem first identified nearly a century ago that seems to insist that cycles cannot have been repeating forever without piling up evidence of their own history. We will get there. But before we do, I want to show you the most beautiful and the most radical of all the no-beginning models, one that does not use bounces or collisions at all, one that takes the cold dead end of our universe's far future and reveals it to be, impossibly, the fiery birth of the next. To understand it, we have to first travel to the end of time. Part 7. The Universe Only Forgets. The strangest idea in this entire video comes from one of the most respected minds in physics, Roger Penrose, the mathematician who, with Hawking, proved that general relativity demands a singularity, and who later won a share of a Nobel Prize for his work on black holes. Late in his career, Penrose proposed something that sounds at first like mysticism, but is built from rigorous geometry. He calls it Conformal Cyclic Cosmology, and he laid it out in a book called Cycles of Time. To understand it, you have to be willing to follow one genuinely mind-bending chain of reasoning. So stay with me, because the destination is worth it. Penrose begins not at the beginning of the universe, but at its end. So let us go there, to the far, far future, almost unimaginably distant from now. Picture the universe 10 to the 100th power years from today, a 1 followed by 100 zeros worth of years, a span so long it makes the current age of the cosmos round down to nothing. By then, every star has long since burned out. Every galaxy has gone dark. All the matter that was not torn apart has fallen into black holes. And then, over almost endless ages, even the black holes have evaporated, dissolving particle by particle through a slow quantum process Hawking himself discovered, until they too are gone. What is left is the ultimate desolation, a universe containing almost nothing but light. Photons, the massless particles of radiation, drifting through an endless, expanding emptiness, forever. Now comes the strange part, the leap that only a geometer would think to make. Penrose asks a deceptively simple question. In that final state, a universe of nothing but light, is there any way to measure size or time or scale at all? And the startling answer is no. Here is why. To measure anything, to define a meter or a second, you ultimately need mass. Mass is what makes clocks tick and rulers have length, through the fundamental constants of physics. But photons, particles of light, have no mass. They do not experience the passage of time at all. For a photon, no time passes between its creation and its absorption, even if it crosses the entire universe over billions of years. A universe containing only massless light has no clocks and no rulers built into it. It has, quite literally, lost the ability to know how big it is or how much time has passed. And if a universe cannot tell how big it is, then there is no difference, no physical difference whatsoever, between a universe of pure light that is unimaginably enormous and cold, and a universe of pure energy that is unimaginably tiny and hot. The two are related by what mathematicians call a conformal transformation, a rescaling that stretches or shrinks distances while keeping all the angles and all the physics intact. To the light itself, with no rulers and no clocks, the immense frozen end and the tiny searing beginning are not just similar. They are the same state, described at two different sizes that the universe itself has no way to distinguish. I know how this sounds, and I want to slow down and defend it, because the instinct is to dismiss it as a play on words. Surely an enormous cold universe and a tiny hot one are obviously different, you might say. One is gigantic and freezing, the other minuscule and searing. How can they possibly be the same? The answer is that words like gigantic and minuscule, freezing and searing, only mean something if there is a standard to measure against. Size is a comparison. Temperature is a measure of how fast things are moving relative to some scale. And in a universe of pure, massless light, there is nothing left to provide that standard. Strip away every massive particle, every clock, every ruler, every object with a definite size, and you have stripped away the universe's ability to distinguish big from small. What is left is pure geometry, pure pattern, and the pattern of an enormous cold light-filled universe and a tiny hot one is, mathematically, the very same pattern. This is the part that requires a real shift in how you think about reality. We are used to imagining that size is absolute, that there is a fact of the matter about how big something is, full stop. Penrose's insight is that size is not absolute when there is nothing massive around to measure it. The far future of our universe loses its scale not metaphorically but literally. The information that would tell you how big it is simply ceases to exist, along with the last massive particle. And a universe that has genuinely forgotten its own size is free to be reinterpreted at any scale at all, including the unthinkably tiny scale of a new Big Bang. The rescaling is not a trick we perform on the equations. It is something the universe itself does, by losing the very thing that defined its size. Do you see where this is going? The cold, empty, infinitely stretched out end of our universe, a place of nothing but exhausted light, is mathematically identical to the hot, dense, compact state of a Big Bang. So Penrose makes the audacious move. He stitches them together. The end of our universe is not an end. It is the beginning of the next. The heat death of one cosmos becomes, through this rescaling, the fiery birth of another, with no singularity, no bounce, no collision in between, just a smooth geometric handoff from the grave of one universe to the cradle of the next. Penrose calls each of these enormous stretches an aeon. Our universe is one aeon. The one before ours was another. The one before that, another still. There is no first aeon. The universe is an endless succession of them, each one expanding, cooling, dying into a bath of light, and that very death becoming the next one's blazing start. Let me place you at the seam, because it is the most extraordinary location in all of cosmology. You are drifting in the final light of a universe that has been dying for an eternity, in a darkness so complete and a coldness so total that there is nothing left to mark one moment from the next. No clock anywhere in existence, no ruler, no scale, only the last tired photons stretching out forever. And then, without anything changing, without any boundary you could point to, that endless frozen light simply is the searing first instant of a brand new universe. The same place seen from the other side, the deathbed and the delivery room revealed to be one room all along. There is a strange consolation buried in this picture, and also a strange terror, and they are the same thing seen from two sides. The consolation is that nothing is ever finally lost at the largest scale. The death of a universe is not an ending but a doorway. The cold, exhausted, light-only future that awaits our cosmos, which sounds like the bleakest fate imaginable, the absolute and permanent end of everything, is in this model simply the far side of a birth, a moment before a new fire. There is no final darkness. There is only handoff after handoff after handoff, world giving way to world, with no last one and no first. The terror is that nothing is ever kept, either. Everything that this universe builds, every structure, every memory, every trace of everything that ever lived and thought and mattered, is erased at the seam, washed out, as the universe loses its scale and its clocks. The next eon does not inherit our stories. It does not inherit our knowledge. It inherits only the smooth, blank, low disorder slate that our ending becomes, with at most the faintest possible markings, the rings from our largest black holes, surviving as almost illegible scratches. The universe goes on forever, but it carries nothing forward. It is immortal precisely because it forgets. Eternity is bought at the price of memory. This is why I gave this part its title. In conformal cyclic cosmology, the universe does not truly end and does not truly begin. It only forgets. At the seam between eons, almost all information about the previous universe is erased by the rescaling, washed out as the old cosmos loses its scale and its clocks. The new eon starts fresh, smooth, low in disorder, carrying almost no memory of what came before. Almost. Because Penrose has made one daring, testable claim. He says that the most violent events of the previous aeon, the collisions and evaporations of its largest black holes, might leave the faintest possible mark on the next, faint rings imprinted in the oldest light of the new universe. And he and a collaborator, Vahe Gurzadian, have claimed to find exactly such rings, concentric circles of slightly unusual smoothness in our own microwave sky. I have to be honest with you about that claim, because honesty is the whole point of this channel. Most cosmologists are not convinced. When others have analysed the same data, the circles look consistent with ordinary random fluctuations, the kind you would expect to find by chance if you went looking for patterns. The claimed signal of a universe before ours is contested, unconfirmed, quite possibly nothing at all. But just think, about what it would mean if it ever held up. It would be a fingerprint pressed into our sky, left by a universe that existed before the one we call everything. A message not written by anyone, but stamped into the fabric of reality by the death throes of a cosmos older than time as we measure it. Whether or not those particular rings are real, the model that predicts them stands as one of the most serious attempts ever made to describe a universe with no first moment. A universe that does not begin, but only, endlessly, forgets. Part 8. Time with Two Heads. So far, every model we have met keeps one thing sacred, even while it dismantles the beginning. Each one assumes that time has a single direction, one arrow pointing from past to future, and the only question is whether you can follow that arrow infinitely far back. But there is a more radical family of ideas, and these do not merely extend the past. They attack the very notion that there is a single, universal past to extend. They suggest that time itself has more than one direction, and that the beginning we imagine is just a low point in the middle of something far larger. To get there, we have to start with a strange feature of one of the most popular ideas in modern cosmology, eternal inflation. The theory of inflation, the burst of ultra-fast expansion in the early universe, was invented to explain why our cosmos is so smooth and flat. But theorists soon realize that inflation, once it starts somewhere, tends never to stop completely. In most of space it ends, settling down into a calm universe like ours, a bubble of ordinary expansion. But in the spaces between, inflation keeps roaring on, endlessly spawning new bubbles, each one a separate universe, forever into the future. This is eternal inflation, and it naturally produces not one universe, but an unending, ever-multiplying sea of them. The obvious question is whether this sea, which clearly has no end, also has no beginning. And this is exactly where the BGV theorem we met earlier was aimed. It was designed precisely to show that eternal inflation, despite being future eternal, cannot be past eternal. The bubbles keep forming forever going forward, but trace them backward and you still hit a boundary. Inflation, the theorem says, must have started. So the most popular framework for endless universes still seems to demand a beginning, which is why physicists who want to escape that conclusion have had to get genuinely creative about the nature of time. Consider a model proposed by Anthony Aguirre and Stephen Grattan. They imagined a universe with a special moment, a single surface of extremely low disorder, extremely high order, sitting in the middle of its history. And from that surface, they let time run in two directions at once. Going one way, you get a universe expanding and growing more disordered, with an arrow of time pointing forward, exactly the kind of cosmos we live in. But going the other way from that same surface, you get another universe, also expanding, also growing more disordered, but with its arrow of time pointing the opposite way. Two universes, back to back, sharing a single low disorder surface, with their arrows of time pointing away from each other in opposite directions. The reason these two-headed time models exist at all is to solve a puzzle that the simple beginning never even tries to address. And once you see the puzzle, the strange solution starts to feel almost reasonable. The puzzle is this. The arrow of time, the difference between past and future, comes entirely from the fact that the early universe was in a state of very low disorder, and disorder has been increasing ever since. The future is the direction of more disorder, but this only pushes the mystery back a step. Why was the early universe so ordered in the first place? A genuine beginning has no answer. It just declares that the universe started out improbably ordered for no reason, as a brute fact. The two-headed time models try to do better. They say the low disorder state was not a beginning at all, but a special middle, a kind of pinch point, and that it is natural for disorder to increase as you move away from such a point in either direction. If you stand at the bottom of a valley, every direction is uphill. If you stand at a moment of lowest disorder, every direction in time is toward more disorder. So, from that central moment, two universes unfold, two arrows of time pointing in opposite directions, each one's inhabitants calling their own low disorder side the past and their own high disorder side the future. Neither is the true beginning. The central moment is shared by both, the way a single mountain pass connects two valleys, belonging fully to neither. The physicists Sean Carroll and Jennifer Chen developed a related idea in which baby universes bud off from an eternal background, with entropy, the measure of disorder, increasing in both time directions away from a central moment. In these pictures, there is no oldest moment, because the question itself stops making sense. You cannot ask what happened before the central surface, any more than you can ask what is north of the North Pole. From that surface, every direction is forward. Every direction is into the future. The low disorder moment in the middle is not a beginning that things came after. It is a special point that two futures emerge from, in opposite directions of time. The thing these models force you to confront is that the arrow of time, the very sense that the past is behind us and the future ahead, may not be a fundamental feature of the universe at all. It may be a local thing, a direction defined only by the increase of disorder in our particular region, our particular branch. And if the arrow of time is only local, then the global cosmos has no single past to trace back to a beginning. The word oldest stops being well defined. There is no one clock for all of existence, no master timeline with a starting tick. There are only directions of increasing disorder, pointing every which way through a structure that, taken as a whole, simply is, with no first moment, because it has no single time in which a first moment could sit. If this seems too abstract to take seriously, consider that we already accept exactly this kind of reasoning about space, and we accept it without blinking. Nobody is troubled by the fact that the surface of the Earth has no edge, no special starting point, no place where it begins. You can walk in any direction forever and never fall off, because the surface curves back on itself, finite in area and yet boundless. We do not lie awake wondering what is at the edge of the Earth's surface, because we understand there is no edge. The two-headed time models and the no-boundary model we will reach in a moment ask us to extend that same comfort to time. They ask us to accept that time, too, might have no special starting edge, that the search for a first moment might be as confused as the search for the edge of a globe. The resistance we feel is not because the idea is illogical. It is because time feels so different from space to us, so one-directional, so much like a river we are being carried down, that the notion of time without a beginning strikes us as far stranger than space without an edge. But that feeling, physicists increasingly suspect, may say more about how human minds experience time than about how time actually works. The flow we feel, the sense of being swept from a fixed past toward an open future, may be a feature of conscious experience rather than a fundamental feature of reality. And if the felt flow of time is partly a story our minds tell, then the felt necessity of a beginning, the powerful conviction that time must have started somewhere, may be part of that same story, a habit of thought rather than a law of nature. This is perhaps the hardest of all the no-beginning ideas to hold in your mind, because it asks you to give up something even more basic than the beginning. It asks you to give up the idea that there is one past, shared by everything, running back toward a single origin. In its place, it offers a cosmos where time is plural, where the beginning we imagine is a low point in the middle, and where asking what came first is like asking which point on a circle is the starting point. The circle has finite length and no first point, and that image of finitude without a beginning of a past that is bounded but has no edge, turns out to be the doorway to the gentlest and in some ways the most haunting model of all. Part 9. A finite past with no first moment. Everything we have looked at so far tries to make the past infinite. The bounce gives us a previous universe. The cycles give us endless previous universes. Conformal cosmology gives us endless previous eons. The two-headed time models give us a past that runs in multiple directions. All of them say there was no first moment because there was always more before. But there is another way to have no beginning, and it is subtler, and once you grasp it, it may be the one that stays with you longest. It says the past might be finite, and there might still be no first moment. Those two statements sound like a contradiction. They are not. This idea comes from Stephen Hawking, working with the physicist James Hartle, and they proposed it in 1983. It is called the no-boundary proposal, and to understand it, you have to let go of the assumption that time near the beginning works the way time works now. In our everyday experience, time is utterly different from space. You can move freely through space, left or right, up or down, but you are dragged through time in one direction, whether you like it or not. Time is the odd one out, the dimension with an arrow, the dimension you cannot turn around in. Hartle and Hawking asked a wild question. What if, near the supposed beginning of the universe, that sharp distinction between time and space dissolves? What if, in the extreme conditions of the early cosmos, time becomes more like just another direction of space? If that is true, then something remarkable happens to the idea of a first moment. As you trace the universe backward toward time zero, time gradually stops behaving like time and starts behaving like space. And a direction of space does not have a starting point the way a moment in time does. Think of it this way. The instant of the Big Bang, in this picture, is not a sharp edge where time suddenly switches on. It is a place where the very notion of earlier smoothly stops applying, the way the lines of longitude on a globe, which run parallel everywhere else, all smoothly converge and simply stop at the pole. To get there, Hartle and Hawking borrowed a mathematical technique that sounds like a sleight of hand, but is used throughout physics, called imaginary time. It is an unfortunate name because it makes the idea sound fictional, when really it is just a different way of measuring time that turns the equations from intractable to solvable. In ordinary time, the beginning of the universe is a jagged, singular edge. But when you re-describe the early universe using this rotated kind of time, time and space become mathematically interchangeable, and the jagged edge smooths out into a gentle, rounded surface with no edge and no special starting point. Hawking's claim was that this smooth, rounded description is not just a calculational trick, but might be the true state of affairs near the beginning, that time really does become space-like there, and the edge really does round off. The technical machinery is hard, but the picture it produces is one anybody can hold, and it is genuinely beautiful. Instead of a universe that comes to a sharp point at the bottom, like an ice cream cone with the singularity at the tip, you get a universe that is rounded off at the bottom, like the smooth base of a badminton shuttlecock, or the bottom of a bowl, or, in Hawking's own favourite comparison, the rounded surface of the earth near a pole. There is no tip, there is no point. There is no place you could put your finger and say, here, this is the first instant, the edge, the boundary. The bottom is smooth and seamless, and that is exactly what the name no boundary proposal means. The universe has no boundary in the past, no edge where it begins, the way a sphere has no boundary, no edge, anywhere on its surface. Hawking gave the perfect image for this, and I want to walk you all the way into it, because it is the cleanest way to feel what no boundary means. Picture the surface of the earth, and picture yourself standing at the South Pole. Now ask the question that sounds reasonable, but is secretly broken. What is south of the South Pole? You can walk south and south and south across continents and ice, and the whole time the question makes perfect sense. But the moment you reach the pole, the question evaporates. There is no further south. Not because there is a wall there, not because there is an edge you would fall off, not because some barrier stops you. The direction south simply ceases to exist at that point. You can stand right on the pole, a perfectly real place, and yet there is no such thing as south of it. The question has no answer, not because the answer is hidden, but because the question dissolves. Now carry that image to the beginning of the universe. In the no-boundary proposal, asking what came before the Big Bang is exactly like asking what is south of the South Pole. You can run time backward, and the question what came before makes sense the whole way until you reach that smooth rounding off where time has become space-like, and then the question simply stops meaning anything. There is no first moment with an empty nothing before it. There is no edge. The past is finite, you cannot trace it back forever, and yet there is no beginning, because the place where you would expect a beginning is smoothly capped, rounded off, boundaryless, like the pole on a sphere. This is a different flavor of no beginning than all the others, and that is exactly why it belongs here. It does not give you an eternal past. It does not give you previous universes or endless cycles. It gives you something stranger and quieter. It gives you a cosmos that is finite in time and yet has no starting point, the way a sphere has finite area and no corner, the way a circle has finite length and no first point. The universe, in this picture, does not begin and does not need to have begun. It simply is, complete and self-contained, with a smooth bottom edge that is no edge at all. There is something almost peaceful in it, after the violence of bounces and brain collisions and dying aeons. And yet, when you really absorb it, the no-boundary idea may be the most disorienting of all, because it removes even the comfort of the question. With a bounce, you can still ask what came before and get an answer. With the no-boundary universe, the question you've been asking your whole life, what came before everything, turns out to be as meaningless as asking what lies south of the southernmost point. It is not that we cannot find the answer, it is that there was never a question there to begin with. And whichever of these models is closer to the truth, every single one of them now has to face the same merciless obstacle, the one problem that has haunted the idea of an eternal or cyclic universe for almost 100 years. They all have to answer to the relentless, one-way march of disorder. Part 10. The thing every model must defeat. There is a reason the idea of a universe without a beginning is hard, and not just because of a single theorem. There is a deeper enemy, woven into the most reliable law in all of physics, and every model we have met has to find a way to beat it. The enemy is disorder, and the law is the second law of thermodynamics, the principle that the total disorder of a closed system, a quantity physicists call entropy, always increases over time. It never spontaneously decreases. It is the most one-directional law we know. You witness the second law constantly, even if you never name it. A hot cup of coffee cools to room temperature and never spontaneously reheats. A glass shatters into 100 pieces and never reassembles itself. A drop of ink spreads through water and never gathers itself back into a drop. In every case, order gives way to disorder, structure gives way to sameness, and the process only ever runs one way. That one-way slide is, in fact, the closest thing physics has to an explanation for why time has a direction at all. The future is, quite simply, the direction in which disorder is greater. Now apply that to a universe that cycles. Each cycle, by the second law, should accumulate disorder. Each bounce, each collision, each aeon should leave the cosmos messier than the one before. And this is not a new worry. As far back as 1934, the physicist Richard Tolman worked out what happens to a simple oscillating universe. one that expands and contracts over and over, and he found something fatal. The disorder builds up cycle after cycle. And because of how that accumulated disorder feeds back into the dynamics, each cycle gets larger and longer than the one before it. Which means, running the sequence backward, the cycles get smaller and shorter still, until you converge on a first, smallest cycle. Tolman's analysis turned a would-be eternal universe right back into one with a beginning. The cycles could not have been repeating forever, because if they had, the disorder would already be infinite, and it plainly is not. To really feel the force of Tolman's argument, think about what an infinitely old cyclic universe would imply if disorder genuinely accumulated each cycle without any reset. If there had already been an infinite number of cycles before ours, each one messier than the last, then by now the universe would have reached the state of maximum possible disorder an unimaginably long time ago. It would be a uniform, featureless, lukewarm soup with no structure, no stars, no order left to spend, what physicists grimly call the heat death. But that is plainly not the universe we live in. We live in a cosmos still abundant with order, still burning through its supply of low disorder, still lighting stars and building galaxies. The very fact that there is anything interesting happening at all is evidence that the universe has not been accumulating disorder through an infinite number of past cycles. Either the cycles have a beginning, or something resets the disorder each time. There is no third option. This is the trap Tolman laid, and it is still snapping shut on cyclic models today. This is the wall behind the wall. The BGV theorem says an expanding universe cannot have an infinite past. Tolman's entropy problem says a cycling universe cannot have an infinite past either, because the disorder would have piled up without limit. Every serious no-beginning model has to have an answer to Tolman, and the most interesting thing about the models we have met is that each one defeats him in a completely different way. The cyclic model of Steinhardt and Turok beats Tolman with expansion. In their picture, each cycle does not simply contract back to its old size. Between collisions, dark energy stretches the universe out by an enormous factor, diluting all the accumulated disorder across an exponentially larger volume. By the time the next contraction begins, the disorder per unit of space has been thinned out to almost nothing. The slate is wiped, not because disorder was destroyed, which would violate the second law, but because it was spread so thin across so much new space that the next cycle begins effectively fresh. The cycles do not have to grow without limit, because the disorder never gets the chance to concentrate. Penrose's conformal cyclic cosmology beats Tolman in an even more radical way. Remember that at the end of each aeon, the universe loses its very scale, rescaled into the beginning of the next. In that rescaling, Penrose argues, the disorder is effectively reset, in part because so much of it was carried away and hidden inside black holes, which then evaporate and, in his interpretation, remove that information from the accounting altogether. The new aeon starts smooth and low in disorder because the old one's disorder was swallowed and erased. Whether that erasure truly works, whether information can be disposed of that way, is one of the open controversies in the field, tangled up with the still unsolved puzzle of what happens to information that falls into a black hole. It is worth pausing to appreciate that the entropy problem is not a weakness specific to the eternal models. It is a problem for every theory of the cosmos, including the one with a simple beginning. A genuine beginning does not escape the puzzle of the low disorder early universe. It just refuses to address it, declaring the improbable initial order a given and moving on. So when critics point at the bounce or the cycle and say, "But you have an entropy problem," the fair reply is that everyone has an entropy problem, and at least the cyclic and bouncing models are trying to do something about it rather than sweeping it under the rug of the first moment. The question is not which model avoids the problem. None of them do. The question is which model has the most honest and promising attempt at a solution. That reframing matters because it changes how you should weigh these strange ideas. It would be easy to come away thinking the bounce and the cycles and the eons are exotic, troubled theories struggling against the clean simplicity of the standard beginning. But the standard beginning is not clean. It carries the single most improbable initial condition in all of science, unexplained, and it carries a first moment that our physics cannot describe. The eternal models trade those two embarrassments for different ones: a contraction phase we cannot see, an entropy reset we cannot yet confirm. Neither side is tidy. Both are wrestling with genuine mysteries. The eternal models are not the desperate underdogs of cosmology. They are serious competitors, fighting the standard picture to something much closer to a draw than most people realize. And the low disorder beginning is itself the strangest clue of all. Our universe started in a state of breathtakingly low entropy, extraordinarily ordered, and that initial order is what has been draining away ever since, powering every star and every storm and every living thing along the way. How ordered was it? Roger Penrose tried to put a number on the improbability of our universe's initial low entropy state, and the number is beyond comprehension. He estimated the odds at something like 1 part in 10 raised to the power of 10 raised to the power of 123. That is not 1 in a number with 123 zeros. It is 1 in a number with 10 to the 123 zeros, a quantity so large you could not write its zeros even if you used every particle in the observable universe as ink. A genuine beginning has to simply accept that staggering improbability as a brute, unexplained fact. The universe was just born that ordered, and no reason can be given. The eternal and cyclic models, for all their difficulties, at least try to explain where that order comes from by appealing to the physics of the cycle that produced it. That is their motivation. That is what they are buying with all their strangeness, the hope of explaining the most improbable initial condition in all of science, instead of just shrugging at it. Part 11. What the sky can and cannot tell us. After all these models, all these beautiful and disturbing pictures of a cosmos that never began, the honest question has to be asked. Can we actually test any of this? Can we look out at the universe and find out whether it began or always was? And the answer is the most important admission in this entire video. Right now, we cannot tell. Not because we are not clever enough, but because of a wall built into the structure of reality, a wall that hides the one piece of evidence we would need. We met that wall earlier, but now we can stand right at it. Remember that the oldest thing any telescope can ever see is the microwave glow released 380,000 years after the hot dense phase, when the universe first became transparent to light. Before that, the cosmos was an opaque fog, and no light from earlier can ever reach us, because it could not travel. That glow is a curtain across the sky, and behind it lies everything we most want to see: the first second, the first instant, the bounce or the collision or the smooth rounding off, whatever actually happened at the moment we call the beginning. Let me put you right up against that curtain. Imagine you could fly outward through space and backward through time, all the way to the edge of the visible cosmos, until you reach that ancient wall of light, the oldest glow there is, pressing on you from every direction at once. You reach out toward it, trying to see what lies beyond, trying to catch sight of the moment of origin itself, and your hand passes into a fog. There is nothing to see. The light simply stops carrying information from any earlier time. Behind that curtain, sealed away, is the answer to the oldest question you have ever asked, whether the universe began or always was. And it is hidden not by distance, not by darkness, but by the opacity of the infant cosmos itself. No telescope built from light will ever pull that curtain back. The answer is on the other side of a barrier that photons cannot cross. That is why the beginning is so resistant to evidence. The decisive moment lives in the first fraction of a second, in the quantum gravity regime, behind the wall of the oldest light, in a place our instruments structurally cannot reach. And to make matters harder, several of the models we have met predict almost identical things for everything we can see. The bounce, inflation from a genuine beginning, and the cyclic collision can all produce a universe that looks, to our telescopes, smooth and flat and seeded, with the same gentle ripples that grew into galaxies. They agree on the aftermath and disagree only about the moment we cannot observe. They are like several different stories that all end the same way, and we walked into the theatre after the opening scene. I want to make sure you really sit with how unusual this situation is, because it is not the normal state of affairs in science. Usually, when scientists disagree about something, there is at least an agreed-upon experiment that would settle it, even if we cannot perform it yet. We may not know the mass of some undiscovered particle, but we know that building a powerful enough collider would tell us. We may not know what is inside a distant world, but we know that sending a probe would reveal it. The disagreement is bounded by a clear path to resolution. The question of the beginning is different. The thing that would settle it, a direct look at the first instant, is hidden behind a barrier that is not merely technological, but appears to be woven into the structure of the cosmos. The early universe was opaque to light, and no improvement in our telescopes can change a fact about the universe itself. We are not waiting for better instruments. We are pressed against what may be a permanent limit. That is a humbling thing for a species to confront. We have mapped the genome, split the atom, photographed the shadow of a black hole, and detected the trembling of space-time from collisions a billion light-years away. We are very good at finding things out. And yet, on the single oldest question we have ever asked, whether everything began, we may be standing at a wall that does not yield to cleverness, because the evidence we would need was sealed away in the universe's first fraction of a second, and can never be retrieved by any eye that works on light. There are, however, a few faint hopes, a few places where the curtain might be just slightly translucent. One is gravitational waves. Unlike light, ripples in space-time itself can pass through the early fog unimpeded, and they could in principle carry information from before the wall of light, from the first instance. Different models of the beginning, inflation versus the bounce versus the cyclic collision, predict different patterns of these primordial gravitational waves, faint imprints they might leave in the polarization of the oldest light. We have not detected them yet, but if we ever do, they could become the first direct evidence that distinguishes a universe that began from one that bounced. The bounce and the cyclic models, notably, tend to predict a much weaker such signal than simple inflation does, so even a non-detection is slowly tightening the noose around some models. The other faint hope is the contested one we have already met, Penrose's claimed rings in the microwave sky, the supposed scars of black holes from a previous aeon. If a signal like that, a genuine fingerprint of a universe before ours, were ever confirmed by the wider community, it would be among the most staggering discoveries in human history. But it is not confirmed, and the honest scientific position is that it is probably noise. It is tempting, faced with all this, to ask which model the experts actually believe, as if a show of hands would settle the matter. But the honest report from the field is that there is no consensus, and the lack of one is itself informative. Some of the most respected cosmologists alive lean toward a genuine beginning. Others spend their careers building and refining the bounce, the cycle, the no-boundary cap. The disagreement does not break down along lines of competence or seriousness. It breaks down along lines of taste, of which unsolved problem a given physicist finds more tolerable, the brute improbability of a created low disorder beginning, or the unconfirmed contraction phase of an eternal one. When brilliant people who share all the same data divide cleanly on a question, It usually means the data does not yet reach far enough to decide it, and that is exactly the situation here. So I am not going to tell you which model is right, because nobody honestly can, and anyone who claims certainty is selling you their preference dressed as a fact. What I can tell you is that the simple story, the one with the confident first moment, is the one option that the evidence does the least to support, precisely because the first moment is the one thing the evidence cannot reach. The beginning is not the safe, default answer, with the strange alternatives arrayed against it. It is one contender among several, and arguably the one resting on the shakiest ground of all, since it depends entirely on trusting an equation exactly where that equation breaks. So we are left in a strange and humbling place. We have at least half a dozen serious mathematical descriptions of a universe with no beginning. They are not crackpot ideas. They are published by some of the finest physicists alive and dead, and we cannot currently tell which, if any, is correct, because the one piece of evidence that would decide it sits behind a curtain that reality itself has drawn across our view. Part 12. The question that may have no answer. We have come a long way from the simple diagram with the little point of light at the left edge, the comfortable picture of a universe with a birthday 13.8 billion years ago. We have watched that beginning come apart in our hands. We saw that the number is real, but the beginning attached to it was never measured. We saw that the singularity is not a birth certificate, but a confession, the place where our best theory goes blind. We saw the wall, the theorem that says an expanding past must end, and then we watched model after model find a way through the gaps in it, the bounce, where a previous universe collapsed into ours, the endless cycles, where every Big Bang is a collision with no first impact, the conformal eons, where the death of one universe is the birth of the next, the two-headed time, where the beginning is a low point in the middle, the no-boundary universe, finite in the past and yet with no first moment at all. And underneath all of them, we found the deepest obstacle, the relentless increase of disorder, the second law, Tolman's century-old problem, and we saw that each model has to pay a strange price to defeat it. So where does that leave us? It leaves us, I think, with a genuine and rare kind of uncertainty, the kind that is not a temporary gap in our knowledge, but might be something more permanent. The people who study this most closely do not agree. One camp, including some who prove the key theorems, believes the evidence points to a real beginning, and that we must simply face it. Another camp believes the beginning is an illusion of a broken theory, and that quantum gravity will dissolve it into a bounce, or a cycle, or a smooth cap, just as deeper theories dissolved every other infinity in the history of physics. A third camp believes, with good reason, that the question is currently beyond our power to answer, and that anyone claiming certainty in either direction is going past the evidence. Sit with that for a moment, because it is genuinely strange. The most basic fact you thought you knew about reality, that it started, that there was a beginning, is, among the people who think about it most carefully, a matter of unsettled debate. Not a solved problem with a few details to fill in, an open question, with serious, brilliant people lined up on opposite sides, and a wall of ancient light standing between us and the evidence that could settle it. There is an old philosophical argument lurking underneath all of this, and it is worth naming because it shows how ancient this question really is. For centuries, thinkers argued that the universe must have had a beginning because the alternative seemed impossible. If the universe were infinitely old, they reasoned, then an infinite amount of time would have had to pass in order to reach the present moment, and you can never complete an infinite sequence of steps. Therefore, they concluded, the past must be finite, and there must have been a first moment. It is a clever argument, and versions of it are still made today. But the models we have walked through complicate it enormously. The bounce, the cycles, the eons, the two-headed time, the no-boundary cap, each one is a serious physical attempt to describe exactly the kind of cosmos that the old argument said was impossible. Some of them make the past genuinely infinite. One of them, the no-boundary model, sidesteps the whole problem by making the past finite and yet beginningless. The ancient logic assumed those were the only two options, finite with a beginning or infinite and impossible. Modern physics has quietly added a third that nobody saw coming, finite without a beginning, and a fourth, infinite but structured, so that no infinite weight is ever required. What this means is that the question of the beginning is no longer a matter of pure logic, something you can settle from your armchair by thinking hard about infinity. It has become a question of physics, of which mathematical model actually describes our cosmos, and that is a question only evidence can answer. The trouble, as we have seen, is that the evidence is hidden. So we are left in the strange position of having turned an ancient philosophical puzzle into a precise scientific one, and then discovering that the scientific one may be unanswerable in practice. We sharpen the question into something physics could attack, and physics walked up to it and found a wall. And here is the possibility that I find the most haunting of all, more than any single model, the thought I want to leave you holding as you drift off tonight. It may be that the question itself, did everything have a beginning, is one that our physics is structurally unable to answer. Not unanswered, but unanswerable. The decisive moment is hidden behind a curtain light cannot cross. The physics of that moment lives in a quantum gravity regime we have no confirmed theory for, and the competing models all fit the same observable universe. It is entirely possible that we are not on the verge of answering humanity's oldest question, but are instead bumping up against a permanent limit, a boundary on what beings inside the universe can ever know about the universe's origin or lack of one. Notice that this is a different kind of not knowing than the one science usually deals in. There is the not knowing of a fact we simply have not measured yet, like the number of planets in some distant galaxy, the kind that better instruments will eventually settle. And then there is a deeper kind, the not knowing of something that may lie permanently outside the reach of any observer trapped inside the system they are trying to understand. The origin of the universe, or its lack of one, may belong to that second kind. We are inside the universe. We are made of it. We can only see the part of it that lies within our horizon, lit by light that has had time to reach us, and the decisive moment is sealed behind a curtain that light cannot cross. It may be that a complete answer to where everything came from is simply not available to anything that lives inside the everything. And yet, here we are, asking anyway. That itself is worth sitting with as you lie there in the dark. A temporary arrangement of matter, assembled out of the debris of dead stars, lasting a few decades, has somehow become capable of looking back across 13.8 billion years and asking whether there was a first moment at all, of building theorems and telescopes and models of bouncing and cycling and eons, of pressing right up against the wall of the oldest light and feeling for what lies beyond it. We may not be able to answer the question, but the fact that a part of the universe can wonder whether it ever began is, in its own way, one of the strangest things the universe does. There is a particular vertigo in that, but there is also, if you let it in, a strange and enormous wonder. Think about what it would mean if the universe truly never began. It would mean that existence itself needs no first cause, no starting gun, no moment of creation, because there was no moment when there was nothing. It would mean that the question we have asked in every culture, in every century, where did everything come from, rests on a hidden assumption that there was ever a time of nothing for everything to come from. And that assumption might simply be false. Existence might not be a thing that started. It might be a thing that always was, with no edge, no first page, no opening note, only the endless middle of a story with no beginning. And you, lying there in the dark, are a brief, intricate pattern inside that story. The atoms in your body were forged in stars, and those stars formed from gas, and that gas was heated in a big bang, and that big bang may have been a bounce, or a collision, or an eon's edge, or a smooth rounding off of time into space, the latest event in something that has no first event at all. You are a temporary arrangement of a universe that may have always existed, briefly become aware of itself, asking where it came from, and finding, at the very bottom of the question, the astonishing possibility that it never came from anywhere, because it never began. The universe does not end and does not begin. It only, endlessly, forgets. And tonight, as you let go of the day, you can rest inside a cosmos that may have been here forever, holding you as it has held everything, with no first moment and no need for one. Let that be the thought you fall asleep to, not a beginning, just the quiet, endless middle going on as it always has.